All right, well, good morning, and we'll transition into good afternoon during the talk. Digital engineering is a fun topic to talk about, especially its future, because digital engineering could be considered the future for most companies that are engaged in what's called digital transformation. So to talk about the future of this subject that is already the future for many companies is a really interesting place to be and to speculate about how technology will change the way that technology itself is created. So what do I want to do in this talk today are a few things. I want to define where digital engineering and digital transformation is globally. I want to make these terms specific. Talk about why companies are engaged in digital transformation and digital engineering and what value they're seeing, and then talk about where this industry is going. So first and foremost, there are a lot of buzzwords in this space. You will hear some leaders talk about digitization of different parts of their company or different parts of their product life cycle. Digital transformation, I think, is the more common term that's being used broadly by industries and consultancies to describe changing the way in which an organization works so that more and more facets of it go digital. There's not usually a lot of definition behind that, which is why I want to go there today. And then digital engineering is a very specific discipline within digital transformation, attempting to make the way in which technology is created more and more digital without having to evoke physical world steps that are costly, time-consuming, and have environmental impacts. I think all of this buzzy space around digital tech is holding industry back from unlocking the full potential. My connection to this field is happenstance. I was running the United States Air Force's program portfolio, including its technology portfolio, and I came across programs that were pushing what we call digital engineering, connecting different models and simulations together from areas of the program's life, like early design, into manufacturing, even into operating and sustaining, and having a complete digital environment to do trades. And so you could start thinking about how much something would cost to maintain or operate while you were still designing it. Engineers could trade information digitally at the model level and make smarter design choices. It did not require the physical system to be built. Well, I was really stoked about this. It seemed like this was a much better way to create hardware that had to have a home in the physical universe that wasn't just software. And so I wanted to learn more about it, and I started doing research about which industries are the most digitally transformed. And the one that jumped to the forefront is Formula One racing. And I was really fortunate that McLaren, a Formula One team in the UK, was kind enough to take me under their wing and show me how they do engineering on a daily basis to win races. And for someone whose background has been in aerospace, it was amazing. Aerospace has a very linear engineering process, going from design into more complete design, prototyping, testing, and then you finally lock the baseline and move into production. Very linear, very physical in nature, and those who have been in aerospace would argue, but that is why aircraft are so safe, why it's an industry that has produced amazing performance from a repeatability and a reliability standard, is that the engineering is very methodical. The idea of turning it completely digital is just foreign in the industry I came from. But in Formula One, engineering was completely digital. As opposed to being able to explore a few designs for a new system, they were exploring tens of thousands of designs every racing season. And they weren't hypothetical constructs. They were all true digital racing cars that could become the physical system on race day. And whether or not they were selected to be printed was merely a matter of the race day idiosyncrasies, the weather, the competitive environment. But all of them were in the hopper competing to cross from the digital world into the physical. Trades were being done at light speed compared to aerospace. In fact, even when the physical car was being built, it was streaming back hundreds of gigabytes, around 300 per race, to improve the models and simulations that birthed the car to begin with. So the digital and physical twins, as they're often called, were not decoupled. They were very much conjoined and interoperating and improving each other. And by the time the racing season ends, the car that ends the racing season is 85% different than the car that began. And that's easy to say. It's mind-blowing if you think about that, if you are an engineer from aerospace or any other hardware-intensive field. Let me say it again. The car that ends the racing season is 85% different than the car that began. That is the kind of agility that we normally see in the world of software, crossing into hardware. And then it clicked for me what digital engineering really was, working with McLaren. It is simply the same agile methodologies, the same continuous integration, continuous delivery methodology that we have so loved in the world of software, eating the world around us. It's simply now possible for hardware. And it is now possible via the magic of integrated models and simulation. We've effectively turned hardware into software via models and sims that are now good enough of sufficient fidelity that we don't need to do physical testing, physical prototyping anymore as our way to validate. The models themselves can do that. And Formula One racing seasons are won and lost based on those digital trades every day. So when I left that and went back to the Air Force, I thought, well, we should do this. We should build airplanes this way. We should build everything this way. And some smart people who I will say were MIT graduates, MIT PhDs, led the charge for us in the Air Force. One of them, Chris Benson, is here today. And then I left the Air Force and joined the private sector, thinking that digital transformation thing, digital engineering thing, sure was fun. I was shocked that so many companies reached out for help in digital transformation, even companies that I was inspired by to do digital transformation in the US government were reaching out for help. And I was like, me help you? I needed you to help me. And I learned through helping industries in and out of aerospace that this is still a very nascent field globally. It's talked about a lot. Just Google digital transformation and see how many hits you get. But 90% of companies are not succeeding. So why? If it's so important and buzzy and impactful, and isn't it impactful to be able to do hardware like software, to have the same design cycles, lower costs, lower environmental impacts? Yeah, it's a no-brainer. It's win-win-win. If it's so impactful, then why are so many companies struggling with it? And as I helped companies do digital transformation, the answer kept coming to the forefront, that integrating models and simulations together to make one consistent ecosystem, often called a digital thread. What I had in the Air Force in a handful of programs, being able to move from the design model of the system and all of the different components, a CAD-like model that captured the structure, and then move over to a requirements model that told me, does that design do what I need it to do in the real world? And then move to an assembly model that tells me about how long it's going to take to make it and what it's going to cost. And then even able to go to a maintenance model where you could have someone who will be responsible for maintaining the system say, Will, this is a stupid design. I'm going to have to get and reach my arm backwards and be double jointed to access that screw. Those design engineers need to put that screw, that panel in a different place. How many times had I seen in government programs where the person responsible for operating said, what engineer made this choice? And now that choice can be found early on. But creating that environment, that digital thread, is non-trivial in many fields. Models and simulations don't plug and play together. They don't give you consistent physics. And as inspired as I have been in my digital transformation journey by the Matrix movies, and I love the idea of like a true digital reality, it's non-trivial to try to get different models and simulations and stitch them together as if they were one metaverse for engineer or one consistent digital reality from an engineering perspective. And so the companies that succeed in digital transformation do so because of one of a few number of mechanisms. They either have really good engineers inherent to their industry that are capable of integrating disparate models and simulations together. And we all know, if you're an engineer here or a scientist here, you know we will not have one model of the universe ever in the foreseeable future of humanity. Right? We do not have the computational power, the memory, so we create lots of different models that capture a piece of the universe around us. Well, the universe being the ultimate computer, the ultimate model in simulation. So we capture a piece of it, we use that piece when the piece is appropriate, and then we don't when it's not. And we typically turn to a different kind of model. And so in most companies, they'll have models that are very high fidelity that can crunch numbers and do finite element type simulation that are used for very specific but very detailed limited analysis that are very different than a high-level model that may tell you about how different systems work together and what the summary benefit could be. So you turn to those different systems when you need them. It's non-trivial to integrate them together in a way that gives consistent answers without lots of subject matter expertise involved. So the industries that have it, like the United States Air Force, are able to kind of pick themselves up by their, by their suspenders, by their belt, and get their tools integrated together. The other group that succeeds knows that they don't have that expertise and they go external. Formula One racing is somewhere in between those two, working with their experts and also bringing in big tech companies to make their models and simulations work together so that the results are consistent and instantaneous, which is why, since we've begun this talk, we are now here at 13 minutes. On average, there's been a part that has been redesigned, retested, and recertified by every Formula One team since we've begun. And the reason is they have integrated models and simulations that are authoritative sources of truth with no people in the loop. So doing that is highly non-trivial. That is why most companies fail in digital transformation. They can bring their different tools together. They can be as different as a simulation from a cost model or an operational model or a bill of materials. You can bring it together and get something that is pretty good, but making real-world decisions where the fate of a business or a sport matters is where the rubber hits the road, and very few companies get there. Good enough is not good enough in this field. It has to be truth. If it's not the authoritative source of truth digitally, then we will go find truth physically. And physically is costly, slow, and environmentally impactful. If we were just talking about digital transformation and digital engineering, then I would end this talk by telling you, so what you need to do, no matter your industry, is either use your internal expertise or hire it to bring all of your models and simulations together into one ecosystem, one digital thread, and then start doing multidisciplinary trades across it. Viciously retire steps that no longer need to be done physically. Treat your digital environment as your authoritative source of truth. And if you can't, that's a data problem. Go collect the data that you need to anchor it if that is possible. That is what Formula One does when they wind tunnel test. That is one and done. They do not collect the same data again and again. If they collect data, it is new data. It is never a repeat of old data on a new car. So do that. Get rid of the physical world, live in the digital world, and win. And companies like John Deere, an amazingly digital transformed company in agriculture, or Formula One racing like McLaren, are examples of what's possible. The United States Air Force and a handful of programs I'll add to the mix. It's not just better, it's magical. It's truly orthogonal to the direction the industry would go by simply improving. I would end the talk by saying you have to do it, because if you don't, then your competition will, and you can be left behind. But this is a talk about the future of digital engineering, so that presumes all of this has happened. Industry has taken on the difficult expense of doing this. So what's next? What's beyond that? What happens like that historians write about? And I can see one example that I'll share, because I do think this will be the thing beyond merely squeezing value out of models and simulations, right? Models and simulations are finally going to come into the spotlight. They're going to join the internet. They're not going to be these pieces of software that are off in a corner on separate machines. They're going to be just like everything else. But the future, I think, you can see in another field of competitive racing outside Formula One, and that's competitive sailing. And one of the things that I do now in the private sector is a bit of consulting for McKinsey, and this is a McKinsey client that's in the public domain. I've gotten to talk with this team, both the technical team that ran it as well as the operational team that got to use the results. That's Team New Zealand's America's Cup team. So another field of competitive racing. So there must be something about competitive racing that naturally leads one to this digital transformation imperative. And that makes sense because it's an advantage. What they did with their digital thread, first they had to build one, digital thread for sailing, which is non-trivial, something that allows you to design a boat and then have all of the sailing dynamics from wind and water, so all of that replicated up to acceptable error digitally, including the mechanics of people actually sailing as opposed to it being sailed, in a world where humans don't actually have to move things around. So rendering all of that digitally, non-trivial but doable and done. But what that team did was something beyond just simply creating a digital thread and designing more boats than their competition and finding a way to win. So they trained artificial intelligence to sail, which Formula One hasn't done. They still put human drivers in the car. But they trained an AI to sail. And what happened was pretty remarkable. You can probably guess, but first the AI learned to sail like people, and then it learned to sail like people better than people. That's probably what you would guess. But what it did next, because it had access to the full digital thread that cuts across all aspects of sailing, is it went back to boat design itself and said, people are not really good boat designers compared to what I see in the data. And the AI designed new boats that defied centuries of sailing logic, and then taught itself to sail them, and went on to create techniques in sailing that humans had to learn from, and Team New Zealand did. They were trained by their AI, retrained, you could argue, to sail, and were never able to beat it again. So AI has eclipsed human performance in competitive sailing. It's just like chess and Go. Humans will never be the best at it again. And I'm surprised it didn't get the fanfare in the media that chess and Go did. Most people thought that Go would be at least a few more years out before the best players in the world would fall to AI. But that happened a few years ago, and the world took notice. And why that didn't happen for competitive sailing, I don't know. But Team New Zealand won America's Cup last year. and they credit AI as the difference maker for them. And I think that's really the future of digital engineering. Yes, creating these integrated models and simulation, a kind of a metaverse for engineers, will have a lot of value. It will save a lot of money, a lot of time, and a lot of environmental impact. But what it's effectively doing is creating an authoritative source of truth for many aspects of the physical world that are faster than real time. And this is what finally gives AI access to physical things, where physical testing is just insufficient because it's too slow and expensive. And so I think the future will be AI finally finding a way to crawl out of the Internet of Things and start mastering the physical world around us. And if competitive sailing can fall and be mastered by AI, what other industries are next? And so the future is one that will either be really, really optimistic with AI opening up doors that we haven't imagined to open ourselves, or very pessimistic because the same technology can be used for bad purposes as well. But we can't wish that future isn't possible. It's happened in one industry. And my prediction is it will happen to others. And while the world is watching the cost savings, the time savings, little by little, AI will become better at living at physical reality than we are. So I guess game on for whether it's the good side or the bad side that wins. Interested in your questions.
Questions from the audience? One here.
Hi, thank you very much for your talk. I enjoyed it a lot. I think I understand how the simulations in engineering for products that are simulating physics are interesting, and then leveraging AI to optimize that. But do you see a future where that kind of ability to optimize competitive advantage is taken beyond the realm of sort of physical things and into more sort of conceptual things? If you think about creating competitive advantages for businesses and, planning, I get involved in strategic planning and we look at all different kinds of things that come together. Do you see a role for AI in that sense? And given you're from McKinsey, I can only imagine what ideas McKinsey might have for AI in that sense.
Yeah, I don't think there are going to be any limitations as long as it's a system that operates based on rules and constraints. I think that's what AI really craves. What chess and Go provide is the ultimate system of rules and constraints. It's a mathematical game. We don't need any construct of physics to define it. Sailing is a game, but it involves physics. You can't do it without understanding Navier-Stokes or simple Newtonian mechanics. But it still operates based on rules, so AI can understand it. I think what has held back a lot of the thinking in this area are self-driving cars, ironically, which require a high degree of digital certification, including models and simulations as the mechanism to do it, to even attempt. And the reason I think it's held it back is from a regulatory perspective, it's arguably one of the hardest problems we could attempt to solve with models and simulation, right? To not just develop a technology that's good enough to drive around us, but then get through the regulatory system, the legal system that's required to unleash it onto the streets around us. I think it will happen. I think the progress, tells us very solvable, but it's less the technical holdups that make me think that it's going to still be a little bit out. It's the regulatory ones. There are many other systems that are far easier to manage, either technically or regulatorily. Farming is a great example. John Deere has stated that they want fully autonomous, fully automatic farming in the near future, and they're not that far away. Is farming something where we could release all of the reins to AI and not have to worry about regulations? Yeah, I can absolutely imagine. It's a very controlled environment. It's, private property. It's not out on the public roads. I think all of the easy problems for letting AI loose, have been skipped. And my litmus test for whether machine learning will master it very quickly or not is it a system where the rules and constraints are easily understood? If they're easily understood and they can be defined, then the system can be gamified. If the system can be gamified, throw enough training at it, and I expect that machine learning will learn a form of mastery that often will eclipse ours.
Thank you.
Dr. Rover, thank you for coming here today and giving us a little bit of wisdom on that. From a digital engineering perspective, your history and your ability to maneuver in and with not just the Air Force, but government writ large, brings it kind of back to an understanding of governance structures. A lot of what I think we're encountering today in the digital engineering, particularly in the model-based systems engineering space, is the systems are getting very, very good at generating outcomes and analytics. The governance structures of the organizations underneath them, it gets a little bit like a blast shield. They kind of put it up and go, yeah, but I got to run it through cyber assessments. And I'm like, guys, cyber assessment, we've done this. How do we move? The utopia that we want to get to, how do we get from the governance of the organization, the human in the loop, to the human on the loop?
It's a good question. I can speak from the industry that I came from in the public sector, from aerospace. So look at aerospace compared to, say, Formula One racing. So in a 30-minute talk, now on average, a Formula One team has redesigned 2 components of their car and retested and have recertified, ready to go, potentially, in the next physical car. How many digital airplanes have been built in aviation? 0. 0 certified. It's never been done. So every airplane that has flown has been physically built and physically certified. And why is that? Well, that's just the way we've always done it. It's the way the governance and regulatory process is accustomed to. As you prototype it, I check your prototype. You test it, I check your testing, and I determine if you're good enough to pass certification. The military has their certification called the 516C. The FAA has theirs. I was talking with a CEO in a large, Fortune 500 company about this pivoting and changing their process to go to digital certification. And the CEO said, but Will, it's not real. Talking about making a decision on certification. And I stopped the CEO and said, but let's think about what real is from a certification standpoint. I know it's real, it's physical, right? If you build a physical prototype, you can touch it, you can often get in it. But from a certification standpoint, what is the real system? What does that really mean? It means that you built something physically, and if you built more than one, they're not the same. They're going to be random and systematic errors in any process that builds things. So you've already introduced error. Then you're going to take it out to some kind of test facility or range, and you're going to test it multiple times. The conditions are not repeatable time to time, so you've introduced more random and systematic error. And whatever equipment, whatever phenomenology you're using to measure it, also has random and systematic error. So your real asset, what it's really doing is turning the real world into a computer that produces data with error statistics. And good engineering means you understand and manage those error statistics. And what does certification mean? It means that error bar falls within acceptable tolerances from a physical consideration. That's what real means from a certification. Real is just data with error that's managed. If you think of it that way, then digital certification is trivial. It's not a different process. It's the same process we've always used. What's different is it's a different form of data with different error, but the process of managing it is the same. What's different is we no longer need reality to be a computer for us. We can allow models and simulations to substitute. And in many industries, they can substitute completely. And for that CEO, that explanation was helpful. because it removes what I think is holding back this industry at the end of the day, is that psychologically it makes us feel better to be able to put our hands on things and say this is real, when you can't do that with a computer file. From a data and mathematics point of view, they're equally real and equally worthy of decision. Time, according to this. I appreciate everyone's attention this morning and hope it's helpful.